scientist working at NASA Ames. I am a planetary scientist and geologist. And it is my pleasure to introduce Dr. Henrik Hargitai. He is a planetary geomorphologist and media historian. He is currently working with me over at NASA Ames as a senior NASA postdoctoral researcher fellow, and where he's been mapping channels and valleys on Mars on the northern rim of Hellas Basin to better understand the water history on Mars and the implications it has for Mars's paleoclimatic history. He's also been interested and has been working to select candidate Mars landing sites for future Mars exploration, in particular for the exploration in human exploration. Dr. Hargitai is also the chair of the International Cartography Association's Commission on Planetary Cartography, and if you haven't, after the talk, you might want to peruse his website, where he has developed maps for children. Planetary maps. They're quite beautiful, and he also developed a map that show the traverse of Mark Watney's travels in the Martian. So do take a look at that. Dr. Hargitai is also a senior lecturer at Eötvös Loránd University in Budapest, Hungary, and he's been there since 2002. And that is also where he received his 2 PhD degrees in earth sciences, specializing in physical geography in 2007, and also in philosophy in 2011. So with that, I will hand the mic over to Dr. Hargitai.
Thank you, Jeannie, for the introduction. So my talk is about the 400 years of planetary cartography, or planetary mapping, how we discovered other planets. And I changed a little bit the title from mapping channels, which is my research project, to mapping exploration zones, that's the future human landing sites, and craters on the moon. So the table of contents is, first I'm going to speak about the past, lunar mapping, and how craters were first interpreted and studied, and then about how I produced a quite simple map of Mars, and finally about the future, about the candidate human landing sites. So let's start at the beginning. The first telescopic map of the Moon and Mars, they look a little bit similar in that the lowest resolution maps are usually include only albedo features. Albedo is the reflectance of a planetary surface, which means that bright spots and dark spots are differentiated. So the first lunar map that was made by using a telescope was made in the early 17th century, and it included numbered and lettered features, similar to the first Martian map, on which the albedo features, dark albedo features, were lettered. So they did not give any names to the features, only showed them with a neutral identification. That's the next step in lunar mapping, the left-hand side of this slide, a beautiful engraving from 1637, and it was made by Claude Mellon, who was the illustrator, the artist, and Pierre Gassendi was the astronomer behind this. This is not a map. This is just a nice picture. And this one is part of a 3-figure series in which Gassendi tried to show the lunar surface, but he used 3 different phases of the moon. Because the lunar map hasn't been invented yet. So it's the next step. The problem is that there are 2 faces of the moon. in terms of how you can visualize the surface. Near the terminator line, this is the terminator line that divides the night and day, the shadows are long, so you can see the topography. Like in this image, you can see from the shadows, the objects from above. So you can see the objects from the side view, even if you're looking at the surface from above. And that's the case near the terminator line. You see the long shadows cast by the crater rims, and that's how you can have a sense of the local topography. You cannot see any shadows here because the sun is high up in the sky, so it's the albedo that is visible on this side of the moon. So you have two different moons. One is that shows the albedo, the reflectance of the surface, which is usually connected to the material that covers the surface. And near the terminator line, the ever-changing terminator line, because it moves, you can see the topography. And Gassendi hasn't invented a method to combine these two different layers. And this, the birth of the lunar cartography had a boom, or it happened at the mid-17th century. 3 different maps has been created, and 2 of them probably independent from each other. And the third was an Italian map whose authors probably knew about the previous 2 maps. And this happened within 6 years. So these are real maps. These are discovery maps also, in which I mean that these maps are not end products. The goal was not to create a map of the moon, but to study the moon. And while they mapped the moon, made this, so the map is sort of side product of a lunar research, studying the surface of the moon to be able to answer the question, what's there? What are those enigmatic features that we can see there? And these maps combine the 2 layers, the albedo and topography. And they also invented the lunar nomenclature, so they added the names, gazetteer of lunar features. And of course, these 3 authors, 3 astronomers, gave very different names, and they used very different philosophies in their naming process. But once the features on the moon are named, we can say that the moon, the lunar surface, is now part of what the Greeks called oikoumene, or the known world, the civilized world, the inhabited world. So the moon became part of the greater human civilization that's ours. The moon became a familiar place just because the surface features has been named. So we know how to refer to them. It's very important, of course, human civilization, in our family. We know how important it is to name someone or something. And the choice of names and the choice of the representation of the lunar features is different for each of the map. This is the first map that was made by Lagrenius, who lived in the Spanish Netherlands, a Catholic country at that time, and even now. So you can see that the choice of the names. Lagrenius was partly sponsored by the king, Philip IV of Spain, who was a Habsburg king, so he named the most prominent crater accordingly, Philip IV. And you can see the name of the queen not very far away, and you can go from the king's crater to the queen's crater through the strait, the Catholic Strait. So it's a very interesting and coherent concept of the lunar feature names. But you can also see that part of the craters has been named after saints, Catholic saints. Others from scientists like Gassendi, I mentioned earlier. His crater is here. Or terrestrial geographic names like Rome, and others from mountains. Well, there is no such mountain on Earth, Austrian mountain, but still, so it's a mixture of commemorative names and terrestrial geographical names. The other map, the very famous map of Hevelius, published in the work called Selenographia, which introduced this word as the term describing the study of the moon. This map is a mirror of the Mediterranean Earth. The terrestrial geographic names are put to the moon the same way, same way as they are situated on the Earth around the Mediterranean. This prominent crater is called Mount Etna, and of course its rim the surrounding area is called Sicilia, and this is, well, it's nearly follows the terrestrial geography. There is Romania here, and the Apenninus mountains or Mons Apenninus, and this is the only name that's still at this spot in today's lunar maps. The others have not been kept. And you see that this concept that, well, you can ask the question, how to name the lunar features. And this was not Lagrangius or Hevelius's invention, because from the Greek times, there was a concept to explain the strange features of the moon, that it's just a mirror of the Earth. Of course, the lunar surface mirrors the sunlight, that we know, but the Greek also thought that it mirrors the features of the Earth as well. So it was sort of natural to try to follow the Greek concept and to name the features according to terrestrial features. And what you also see is that how they visualize the topography of the lunar surface, similar to the terrestrial maps that try to reflect the local topography. They included mountain ranges, and this is a hand-colored version of the originally black and white map, but you can see that it's quite clear that these are lands and the blue ones are seas or lakes. So it's like the Earth, and this map communicates a preconception of the lunar surface, that the lunar surface in fact is just like the Earth. It has seas like the Earth, it has islands, it has mountain ranges, so it might have implications on lunar life as well. But Hevelius also made a second map in his work. That's an albedo map. So while that's a topographic map with nomenclature, that's in today's terminology, that's an albedo map that shows the lunar surface in full moon phase. And if you compare these two maps to the two sheets of the USGS lunar map that was published last year, you can see that not very many things have changed in these 400 years. We still have an albedo map separately, and we still have a topographic map separately. Even the colors are more or less the same. Of course, what's different is that Hevelius's map was the cutting-edge research map of those times. while this USGS map is in fact but it's made for education and public outreach. So it's actually not really used by scientists to study the moon. It's an end product, it's a nice sheet, and you can invent several ways to use this map on your room, in your room. And the third map, which is the most important of these three, is the map by the Italian Grimaldi and Riccioli. And Grimaldi was the astronomer behind the map, and Riccioli was who invented the names and the system of the nomenclature. And the names are quite familiar if you have seen the lunar maps, because it's pretty much how a lunar nomenclature looks like today. So that was adopted by the International Astronomical Union as the official names. Most of them are the official names today. But you can also see some names that has been dropped. So this prominent crater is called Copernicus, which is interesting in the view that this map appeared as part of a book called New Almagest, and Almagest was in fact an anti-Copernican work, and still the two authors named one of the most prominent craters after Copernicus. This is a map I've made a few years ago from topographic data. So this is how this same area looks like in a contemporary map. Yeah, it's a little bit different. So because at that time, this map just reflects what Grimaldi observed on the moon, but he didn't know the nature of these features. Now from topographic data, we know the nature of these features. We know the topography, and we think we know the geology also behind those features. Another interesting concept behind the nomenclature is the dichotomy between the terra, or the lands areas, and the Maria, the seas. Because originally there were seas and lands. All the terra names have been dropped by IU, so we don't have any regional scale names for the highlands, which I think was not the best decision from IU. And it was a quite coherent system. You see Terra Vitae here, the land of life, and you see Lacus Mortis, the lake of the dead. So it's a coherent system. Terra Siccitatis, or the land of dryness, and Mare Imbrium, the sea of the rain, the bay of dew, the land of frost, and the bay of the rainbow. So all these names come from meteorological features. And why is that? It's because again, the ancient Greek concept was that, at least Plutarch had a work in which he described the moon as when the moon is full, most dew falls because the light of the moon is moist. That was the general, not geological, general philosophical concept of the nature of the moon. So the moon and the moonlight was associated with wetness and moist and clouds. That's why most of the names on the moon come from this theme. The Terra and Mare system comes from the very first map, but the names, again, are very different. These names, we call them descriptor terms today, are the same, but the concepts are different, like Terra Sapientiae, the the land of wisdom. There is one feature on the moon, on these maps, that has similar names. These are the Caspian Sea here, and the Caspian Sea is also here, which probably, again, goes back to this Greek concept of the mirror-like lunar surface. So it's not exactly the same feature, but almost there. So this probably, because these two maps were made independently, probably the astronauts knew that there was some ancient nomenclature of at least some of the features that were preserved by these maps that are not preserved in old Greek texts, but we can know it from these maps. And this tradition of naming features after terrestrial features is still part of the IAU nomenclature. You can see Ontario Lacus here, which is on the southern polar region of Titan. So a map has names. They have some sort of visualization of the surface, and they have a coordinate system. What was the original coordinate system of the lunar maps? Again, these were made independently, so there are several concepts of how to apply a coordinate system for the moon. This Hevelius's map used a polar coordinate system, 360 degrees around the disk of the moon, but it was centered, not the poles as the polar coordinates are centered today, but it was centered at the center of the visible near side of the moon. But still, you could make measurements, or you could determine the coordinates of a feature. The Grimaldi and Riccioli's map is very different. They used octants, 1/8 of a circle, and it was not just a coordinate system, but it was also connected to nomenclature. The first octant contained most of so they had the craters named after the ancient Greeks, and as we progress towards the last octant, we go further in time to reach finally the contemporary scientists of their era. So it's like a time travel back in time to the first octant and to the present at the last octant. You can also see that these authors try to preserve their own names of the moon. There is Riccioli here and Grimaldi here in Riccioli's and Grimaldi's map, but there is also Hevelius here. And Hevelius's map is a geographic map, so it was not possible to put his name on his map, but the IAU still preserves the map, the name of Hevelius here, and Riccioli and Grimaldi at the very same spots. So these are the same craters. And Langrenus also had a crater named after him on his map, even a sea, Mare Langrenianum. The name of the sea changed, but Langrenus crater is still there. So these are a little bit confusing that at the 17th century there were at least three very different maps, very different concepts, very different surface feature visualizations, and it lasted for at least one century. That's a map of the moon from 1742, and there was no way to show the surface of the moon in one map, because the Hevelius map was used in Protestant countries as the official map of the moon, and the Riccioli map was used in the Catholic countries as the official map of the moon. So if you wanted to be politically correct, you had to display both maps on your publication. So that's about the first lunar maps, and now we move on to discover the first extraterrestrial planetary bodies. In other words, the planets of the solar system and the moons of the solar system in low resolution. And it's again, what I'm trying to show you is how to interpret what you see through the telescope. It's not easy. So these are the first views. It's a very famous figure, the first views of Saturn. We all know that Saturn has rings, but at that time it was not at all expected to see rings around a disk, around the planet. So there are different understandings of the view, the scene through the telescope. Is it two side moons? Is it a solid body connected with the rings, or are the rings independent from the central body, or is it something very strange? It had to be learned to interpret this view correctly. And an example from today of how to interpret low resolution data is this strange star that which has a light curve that shows the dimming of the star. It's called the WTF star in popular literature, and it's also known as the alien megastructure. Maybe a month ago, I've read an article that said that it might be a not correct interpretation of the data, that it's dimming more than other stars. But you can see the artist's concept is from a comet-like planet to the alien megastructure, has a wide variation, just like in this first early concept of the nature of the rings of Saturn. And of course, after 100 years, Huygens could draw the, let's call it, correct interpretation of the ring of Saturn, but it still looks like a solid object. It still needed some time to figure out the nature of this strange feature. And if we go again to find something similar from today's literature, you can see this this oversized ring, which might not be even be a ring, but it's a proto-exosatellite disk, similar to protoplanetary disks, in which the moons of this central planet are accreting right now, because it's a young star. So it has again many interpretations of what we see. Again, this is an artist's concept. It's not a photograph. Now, let's see what are these enigmatic objects on the moon that are circular, how they try to figure out the origin and the nature of these strange circular features that has no one ever seen similar on the Earth. There are different types of craters. The simplest type is a bowl-shaped cavity, which was first observed by Galileo Galilei when he first used his telescope to observe the features in the sky. And he did not call it craters, he called it macula minor, or small dark spots. So it was absolutely scientific and neutral term for these features, and of course he didn't know what they are, so that's a very good way to name, give a descriptive term for these features. So what are these craters? the most accepted theory is that was at that time means from the 17th to the mid 20th century, that these are volcanoes. There are different sizes of these craters, of course, and some of them might have been formed as large, not eruptions, but bubbles of magma, or just really eruptions of a explosive volcanic event. And the rim around the crater, which is not very visible here, is might have been or a ejecta of the volcanic material. That was the idea of Schröter. And at the mid 19th century, it was still thought to be one of the greatest peculiarities of the moon. Nobody knew what they are. Elgar called them bizarre forms, but still they were thought to be volcanic. A larger group of these circular features has been called walled plains, and amateur astronomers still call them walled plains. Galileo called them macula magna antiqua, ancient large dark spots, these features. They are named lacus, lakes, on the maps. Hooke divided these features into the central plain, and that was the valley, and the rim, that was the hills. And Schröter, who made a very detailed mapping of the moon, called them walled plains. That was in German. That's the origin of this name. And later, probably the most detailed maps of the 19th century, until the late 19th century, was made by Beer and Mädler, a German pair of astronomers, who called them ringed mountains. So the feature was not the crater, but the ring around the crater. It's like the names of the streets. We name the streets in the Western world, but in Japan they named the blocks and not the streets. So here, until the 19th century, the feature was the ring mountain and not the crater. And Beer and Mädler, who, as I said, made the most detailed mapping of the moon, correctly concluded that if we say that these craters are volcanic, it's probably not right if we compare them to terrestrial volcanoes, because these lunar craters are just too large to be similar features, and they have too wide floors if we compare them to a terrestrial volcano. So comparative planetology has been born. As we go on to the end of the 19th century, the walled plains had another interpretation. They are alluvial deposits or marine deposits, so they are dried lakes or seas. And at the very end of the 19th century, a new idea came up from Thomas Elgar, who said that these might be basaltic plains. And another one early in the 19th century by Pickering said that these might be lava-filled calderas of shield volcanoes. Again, still a volcanic interpretation, but it's not the explosive crater of a volcano, but a collapsed caldera. And calderas were not known in the 17th century. They were discovered much later. This is a nice figure showing the formation of a lunar crater with a central, what we call now central peak. That's a photograph, and its explosive volcanism in which the rim forms from the ejecta, and the central peak forms from a central volcano, a cone. And I forgot to include the image of the volcanoes of Io here, but if you think of the Ionian volcanoes, these umbrella-shaped plumes of volcanic material are really just like here. It's quite similar. So the problem with this volcanic interpretation of the central peak craters was that they used the wrong terrestrial analog. They thought they used a good one because in Italy, the Vesuvius is, well, from a satellite image, it's not identical, but sort of similar. There's a central cone, and there is a caldera, a rim around that. That's the Somma volcano, and there's a collapsed caldera on the top of which there is the Vesuvius. But again, that's not the right analog. So morphology alone is just not enough to interpret similar features. So that was the end 19th century concept of different circular forms. Some of them are volcanic, some of them are non-volcanic, dried plains. And there is another size category, the Maria, or these large dark spots, some of which are circular. And the classic view has been preserved in a letter from Kepler to Galilei, who wrote, Kepler wrote to Galilei that the dark spots are probably seas, and the bright parts of the moon are lands. Again, from an analog of terrestrial observations, you can see that the lakes are darker than the land, the continents, land areas. Again, Beer and Mädler thought it's unlikely that these dark spots are containing liquids, because the surface topography is rough, and for a liquid surface we don't expect it to be rough with holes and shadows. And they couldn't observe any clouds or rain or snow or any sign of precipitation there. So if there is no atmosphere, they couldn't observe an atmosphere as well. There probably are no seas, because without an atmosphere you cannot create a liquid on the surface, a volatile liquid on the surface. So Beer and Mädler concluded that there is a complete and total difference between the surfaces of the Earth and the Moon. At the second part of the 19th century, they had many very different ideas of the nature of these mare surfaces, from deserts to prairies, alluvial deposits, to basaltic material. But at the middle 20th century, the first idea of linking these features to an impact event came from Ralph Baldwin, who said that these might be these basaltic plains might have been produced by an impact event. And the last very interesting idea was that these plains are covered with a layer of very fine dust. It was called the gold dust, because it was proposed by Gold, and it had implications on the early space programs, because at NASA they were really concerned that the first spacecrafts which were designed to land on the moon, so they could sink into this layer, this thick layer of dust. It didn't happen, but there was a concern. So again, even in 1967, Kuiper said that Mars surfaces has been an object of too much speculation. So we are 2 years before the lunar landing, and they still didn't know what the Maria are. There was a paradigm shift at the end of the 1960s in lunar geology, thanks to the landings on the moon. And before that, we could, of course, there was much, it was not, they knew that there are some missing elements that we cannot make coherent picture of the lunar evolution, the surface. But still, we can say that there was what I called the wet moon paradigm, which included several evidences that the moon was or still is wet. Like we can observe sinuous channels, which are also called rills, on the moon. And we can interpret them as dry riverbeds because they're just like rivers. They meander like terrestrial rivers. So that's one evidence for a wet, at least past of the moon. They might be dried, but the channels are still there. They saw these flat and dark surfaces within the walled plains and the Maria. These could be interpreted as dry sediments from seas or lakes. The craters offered another evidence for a wet moon in which the moon is full of craters. So if we interpret them as volcanoes, that means that the moon is or has been full of active volcanoes. And we know that volcanoes, the gas, emit gases which include water vapor. So that it's quite obvious if we look at the craters as volcanoes that the moon had to have an atmosphere which had to have water vapor in it. So that's again an evidence. And how do we know that these are in fact volcanoes? Another evidence for volcanic origin of the craters comes from meteorites, because there were falls of meteorites known for a long time, and you can even hold it in your hand, and that piece of rock came from the sky. So one way of interpreting these pieces of rock is that they came from the moon. Where else? These are ejecta from lunar volcanoes. This concept was rejected in the mid-19th century, but until that, it was a valid interpretation. Vegetation could be another way, an evidence. First, there was an astronomer whose name was Hargitai, who actually observed them, not only vegetation, but even cities and different structures and even the inhabitants of the moon. And that was quite problematic for his reputation later. But more modest vegetation-linked evidence is that the crater floor texture was thought to be bush-like by Hooke, who was a prominent astronomer, and the color of the crater floors was consistent with some kind of vegetation that was repeated for Mars later. And the existence of vegetation was even supported by this volcanic interpretation of the craters. So they all fit together. That's the problem, that we can create a paradigm in which it seems that everything fits together and we can find evidence, linked evidence. We can link the evidence together to have a seemingly coherent view of the nature of the moon. Of course, craters are impact features. And that was also in the literature, and they knew about this concept that they might be impact features. But again, the problem was that this concept was first proposed by Gruithuisen, and that was not really a good credit for this concept. The problem was it was also the most problematic thing was that they knew no projectiles that could produce these craters. At that time, the space was empty. So if you say that the moon is full of craters and these are all similar and these are all impact features, there's just no projectile, there's no body that could make these features. That's a fundamental problem. But how about comets? Comets are moving objects in the sky. But interestingly, they thought that if a comet hits the Earth, and there was a famous book, a fictional book by Camille Flammarion, who was an astronomer and also a author of proto-science fiction. He described the end of the world, and the end of the world was caused by the impact of a comet, but it was not an impact, it was an approach, and it caused the terrestrial atmosphere to burn, but there was no impact, there was no hole, it was not so they didn't even think about the possibility of linking the comets to craters. It's a very different kind of body. The basins, the nature of the basins had also, so it was difficult to figure out what they are because they were all flooded by lavas. So they are impact craters, it's just large impact craters. But you cannot see that they are impact craters because they are flooded. Except for this one on the moon, but that's on the side of the moon. It's not visible from the Earth. It's not on the near side, it's on the edge. And the first evidence for linking these basaltic plains to crater forms came from this experiment in the 1960s, in which the lunar globe, the photographs of the moon, were again photographed from the side, projected into a sphere, and it was visible that at least this half of this large impact basin is the part of a circular feature, and it was immediately recognized that that's a large basin, that's a large crater, and probably these features are similar, so these are impact craters. So the original theory that these are volcanic features is right. That these are seas is also right, it's just not a sea of liquid water, it was a sea of liquid lava, and it is covered by dust. But the gold theory was that dust came from the highlands, and we know that dust is produced in situ. But still, these are half-truths. It's all partial truth. And it took more than 300 years to figure out what they really are. Today we have similar enigmatic features on Mars. So these are the craters. And these are these circular features with cones and craters, pits and rings on Mars, which you can see that these are the competing theories that try to explain their origin. These might be different features, or these might be similar features formed under different, formed in different environments. And the theories range from volcanic to glacial to sedimentary to spring mounds. So history repeats itself. It just takes time to figure out, but craters, the enigma of craters has been solved, so probably this enigma will be solved in the future. So the third part of this talk is about Mars mapping today. I call it research through mapping because, again, the goal is not to produce a map. The goal is to understand the geology of Mars better, and the tool for this is to produce the map. We start with a base map, and this base map is, the theme is infrared image mosaic of the surface of Mars. That's a 1 kilometer per pixel resolution photo mosaic. Then we add topographic data from the MOLA instrument. It's a laser altimeter data set. Then you add high resolution images from another camera, the CTX, the context camera, and you can start mapping now. We have the background, the base layers. In geological mapping, you trace contacts, which is the boundaries of different units, different geological units, which might be different in their texture or pattern, topography, color, albedo, or thermal inertia, which is basically that these are cooler or warmer at a particular time of the day. So once you have traced all these contact lines, you get the geological units that formed at the same time in the same process. You can color them to separate them by, to classify them, separate them by processes. The yellows are impact forms. These are the ejectas of the craters. The pink and blue ones are volcanic. The brownish ones are old impact surfaces. But if you want to know their ages, when they formed, you have to count all the craters that have been produced on these surfaces. And by counting the craters, you will get an age. More craters means older surface, less craters mean younger surface. And then you can name the units using the age, like Noachian, that's the oldest unit on Mars, and the description of the material, like Noachian ejecta. Next step is to map the location features, the point-like features in this scale. Then you can add, of course, that takes quite a time to trace all these channels. You can add linear features, and the colors suggest they are rivers. Who knows? They are channels, they are valleys, they are not streams, they are paleo streams or paleo rivers, probably. But these are just channels and valleys, or old dried riverbeds. You can add more structural features like wrinkle ridges or troughs, graben, other linear geological features, and surface features like these are knobby terrain, which means that this terrain has lots of knob-shaped feature on it. And if you add all these differently classified features, you end up with this view. And I would not, again, it's not a map. I call it a display of geospatial data, but it's still not a map. And you can see the difference when from the beginning of the mapping, that's that's the view initially, and that's the final view. You added information. It's still the same, but a photo map is just not enough to interpret the surface. You need to map it, and that's the map output. That's again good for an illustration in a research paper, but that's not good for any further research because it's a static, it's a JPEG, it's a nice picture that shows you the general view of this surface, the general characteristic of the surface, but you cannot really analyze it. It's just a figure. If you want to analyze and use the map, you have to make a dynamic map, a geographic information system, which looks like this in this view. And you can mix your own mapped layers, like what we did in these previous slides. You can add layers from previously published data, like the USGS geological map of Mars from this map is integrated into this digital map. And you can add other layers from other research papers, so from other workers who worked on mapping different features. And the totality of this multi-layered, multi-thematic map is the one that you can work with to find new patterns, new feature types, or to create new theories that explain the surface evolution. And we have 3 minutes to find exploration zones in this area. So it's again, it's how we use these maps, how we analyze the resulting data. We first exclude the too steep regions. Then you include those features that probably contain ice, which means water for surface operations. And these water-containing regions will be the centers of the future exploration zones because you always need water. You cannot take it from the Earth. So you draw a 100-kilometer radius circle around these places, but you still need to determine which is the best place to land. And if you want to determine that, you have to include all these different features that are necessary for living there and that are interesting enough for research. And you determine which circle includes all the needed features and which circle includes the most diverse range of different features, and you end up with this map that this circle is the best for exploration because this has the most variety of interesting surface features. But if you close enough, so that was an automated evaluation of these maps. So that's the center. That's where probably the water is, which is ice. This might be a good landing site, but is it good enough? And you can start thinking about it. This water-containing deposit is in a valley. Are you going to be strong enough to drag all these rocks, ice from the valley to the landing site? So you have to manually analyze the surface and compare them. It's not just automation. And the mapping takes quite a long time. The mapping of this region that I showed you takes 1 year for one worker, full time. The next few years is for publishing your results from the science results of this mapping. And if you want to publish this map in a official USGS geological map, the review and corrections take another 1 year, which is very good because these are controlled maps, reviewed maps. So there is no mistake in this map. So it has to be reliable. And it has to be prepared for publication. That's cartographic line work, which might take another year. So in summary, planetary maps are documenting the surface features and are also tools for exploration of the surface. They have different types of planetary maps made before, during, and after the mission. And they also have to be easy to read and aesthetically pleasing, which means that they need a standardized symbology, for example, and also creativity. But the ultimate purpose of the maps may seem to be just to produce more maps. Okay, you can find more maps from the past and the present in this website, and I thank you for your attention.
Henrik, thank you for giving such a nice talk on the history of planetary mapping, and also in honor of, this is the International Map Year. So what I'd like to do now is open it up to people who would like to ask questions, and wait for the mic so that we can record your question.
Hello, thank you. Could you go back to the previous slide, please? Yeah, that one. So next target, Kuiper Belt objects and exoplanets. What do you need to have a view of an exoplanet that is more than 1 pixel?
I think that right now we don't have any instrument that could take any such picture. So that's, let's say, it's the far future next target. But once the Kuiper Belt objects are, or at least a few of them, they're of course quite a lot to map. So once the solar system objects are mapped, it's obvious that the next target to resolve in more than 1 pixel is the exoplanet. If, of course, the largest are probably gas giants, so there is not too much thing to map there. But yeah, it's going to be difficult.
Any other questions?
Thank you. That was fascinating. You put your emphasis quite rightly on morphology and albedo, and brought us through a discussion up to the Apollo landings and the moon. And I think you implicitly said, but didn't explicitly say, that with the lunar work, there was a tremendous influence from theory of how the moon was created. So we had these two very different worldviews. We had the chemists saying it was a huge meteorite, and then we had the astronomers saying it was some sort of a volcanic object. So, you know, the Kuiper-Urey controversy. So whichever of those two theories, and they were, you know, at least on the Urey part, were pretty theoretical, you were getting very different concepts from which to work. So when you saw something very different. So Urey says this is a meteorite full of carbon, full of water, full of life potential, and Kuiper says it's an extinct volcano, it's a differentiated object, a melted object, totally incapable of sustaining any form of life or water or organics. So I think there's this aspect too, which I say you kind of implicitly touched on, but how do you view the moon determines to some extent what you see.
Yeah, you always have a preconception when you see something, so you cannot escape from what from all the theories that you already learned, and it's also might be related to language, that you use words to describe the features, and words are necessarily make classes or types which might not be there. So any classification divides the continuum of reality into discrete classes. So it's always there, and you work in a paradigm. Yeah.
Thank you.
Great presentation, thank you. I just have a question about Mars. There's a lot of talk that we will go there, and maybe even private companies go there. So the question is, do they use the same data for the map? And when they ever get there, are they going to feed that data back? Like when it happened in the moon that we realize, so is that open?
Of course, we don't know what will happen if private companies will start mapping other planets. The current data is public, so any NASA data is on the public domain. So if private companies want to use that, they can. But if private companies start to make their own data sets of other planetary surfaces, that situation may change. We know from Japan that the Japanese lunar landing was partly sponsored and paid for and made by the NHK TV company's instrument, which pictures are copyrighted. So it might be the first of these future data sets that are not free to use. Yeah, that will be a problem. And private companies might not think that they have to use the international IU's nomenclature because they have different ideas. They may publish different. That's science fiction. We don't know. It might be problematic. Mm-hmm.
You mentioned it taking a year to do that small area. What other things are you using to perhaps automate it for the whole Mars? Machine learning techniques, perhaps, to find landing sites.
But for landing sites, it's still under investigation how to even evaluate the proposals. We have 47 proposed landing site circles, and we have just started to evaluate them. It will take a lot of time because we don't have. I believe that we don't have enough data to evaluate those sites yet.
My question is about Eratosthenes, the crater that Pickering viewed and saw swarms of insects in. And I'm wondering, can you tell us how could he possibly interpret, what features did he interpret as swarms of insects?
I'm not sure about this particular interpretation, but there are crater rays around many of the lunar craters that are white and linear features radiating away from the brightest and youngest craters, and there was again several different interpretations for those again enigmatic features, what can cause bright rays to appear around craters. That might be the interpretation. Yeah.
Okay, any other? Okay, well, Henrik, I'd like to award you a SETI.org talk from the
Thank you
SETI
very much.
Institute. And let's thank Henrik once again.